So today I'm going to tell you briefly about some work we have been doing on data-driven subgrid-scale modeling, SGS modeling, and with a particular emphasis on issues related to stability and generalizability. And I'll show you some results that we have with a two-dimensional turbulence test case. So we already heard a number of great talks about why we need better weather and climate models, and why we need subgrid-scale modeling, and why we need better subgrid-scale models. So I'm going to skip the introduction pretty much, but in a nutshell, we know that the climate system is a multi-physics, multi-scale system, even though in many cases we are interested in the variability of the large and slow scale variables that collectively I show them with X. I can't see the mouse. Do you see the mouse? No? Okay. Even though we are usually interested in the large scale variables, we can't ignore the effect of the small and fast scale variables that I collectively show them with Y. And basically, currently, we don't have the computational resources to resolve all these scales explicitly. So, of course, the traditional approach has been that we try to formulate our governing equations that are closed in terms of the large scale processes X. And these equations we can afford to solve on coarse resolution grids. But to do this, we will need some closure schemes for the subgrid scale processes, something that would connect the large scale and the small scale variables, basically something that relates Y to X. This is, of course, a very crude representation of what SGS closure model does. But basically, the essence is we can use that to close the equations just in terms of X. Now, of course, there has been a lot of work in the past few decades on developing physics-based SGS models, and they're not perfect. So as a result, in the past few years, there has been a lot of interest in how machine learning might help in developing data-informed or data-driven SGS models. For example, one approach has been to try to learn the relationship between X and Y in high-fidelity data using some machine learning technique, for example, using a neural network, and then use this as the closure model by coupling the neural network with the numerical solver. Now, of course, like any application of machine learning to weather, climate, turbulence modeling, there are questions, challenges, and looking in another way to them, opportunities. And some of them are basically about what are the best ways to even use machine learning for these kind of problems. Even if you know that you want to do subgrid scale modeling, there are different ways to do this. And we already heard about some of the different approaches earlier in the day. Even after that, we have to decide what is the best method for the problem that we are interested in, how to deal with the fact that in many cases we do not have a lot of high quality data to train the machine learning methods, how to incorporate the physics, and how to interpret the data-driven models. Those are also challenges. You might recognize that some of the earlier talks also talked about these challenges, especially the talk about by Luke. He mentioned some of these challenges and talked about them. Even beyond these, there is always the question of generalization. And specifically here, I'm talking about extrapolation. We might train a good data-driven SGS model that works for a given climate system, for a given flow. But then if you change the forcing on the system, if you make it more chaotic, if you are just looking at the turbulent flow, if you increase the Reynolds number, the machine learning method, the data-driven model might not work that well. And many people have already seen this in their work on subgrid scale modeling. Even after all these, there are instabilities that many studies have found. Stefan talked about this in his presentation. So in many cases, we have a good data-driven model, works very well offline, but then once it's coupled with a numerical solver, basically once we do an online test, it blows up. So my group has been interested in a number of these questions, but today I'm going to briefly talk about some work that we have done on the issue of generalization, specifically how transfer learning can be used to improve generalization, and also some work that we have done on instability. So as a test case, we are looking at the two-dimensional turbulent flow. So here, as you see in the equations, we have omega, that is the vorticity, that is linearly related to psi, which is the stream function, that you have the nonlinear term, the Jacobian term, and we also have the Reynolds number, that is the parameter that describes this system. Here we are looking at decaying turbulence. So we start with a energy spectrum, that is the black line in that figure. And then after some time, when the flow evolves, it gets into this self-similar regime, the blue and red lines, that it has the K2-3 slope, and you see the evolution of the flow in this movie. So here, these are the results from directly solving these equations from direct numerical simulations, which requires basically a fine grid. So here we have almost 2,000 squared grid points at the Reynolds number of 32,000. So now we want to do larger simulation, which basically means that we take these equations and we coarse-grain them and filter them. So here, overbar means filtered and coarse-grained variables. The filtering, coarse-graining, there are different ways to do it. We might use a spectral filter, a low-pass filter. It might be a Gaussian filter. But basically, what happens is once we filter the variables and coarse-grain them, we know that we can write this equation almost in terms of only the largest scale and the resolved variables, only in terms of the overbar, the variables with overbar, which are really that capital X on my first slide. But still, there would be a residual term, a term that is, I'm going to call it pi, the SGS term. This is the term that we can't explicitly write in terms of the resolved flow. You can rearrange these and write this term basically in terms of the prime terms, in terms of the eddy fluxes. Now, the advantage of doing LES rather than DNS is obvious. For DNS, we need very high resolution grid and small time steps. In this problem, for example, at the Reynolds number of 32,000, we can use an LES grid that is 8 times coarser in each direction and a time step that is 10 times larger. So already like 640 times fewer degrees of freedom that we can use for the simulation. But of course, the problem is how to write pi, the SGS term, in terms of the resolved flow. Now, again, there has been a lot of work on physics-based models, for example, from early work by Smogorensky, because on average, the role of the eddies, we know that it's diffusive. People have developed these eddy viscosity models that basically we have an eddy viscosity parameter, Laplacian, that we plug this in here, and we have a closed equation in terms of the resolved flow. But I will talk about some of the issues with this kind of physics-based parameterization on the next slide. So the idea of data-driven parameterization, as I mentioned before, is can I represent pi only in terms of the resolved flow that I learn the relation, for example, using DNS data, using a neural network. And the results that I'm going to show are from this paper that is available on arXiv. And there are a bunch of things in this paper. I'm going to talk about 2 of the type of analysis we did. One is about transfer learning. The other one is about backscattering analysis and the issue of stability. So just to give you a general idea of one of the major shortcomings of many physics-based models is that they are basically only account for diffusion, and they don't account for what's called backscattering. To give you an idea of what this is, we can define a subgrid-scale transfer function T, that I'm going to define it like this. It's basically the pi term times the Laplacian of omega bar. Now, for diffusive models, for example, for Smogorensky type models, we know that pi is the eddy viscosity times the Laplacian. So it's always non-zero. So it can only be positive or zero. And when it's positive, it's basically doing diffusion. It basically means that the eddies are diffusing the energy or entropy of the large scale flow. Now, to see better in the DNS data what the sign of T is, here I'm going to show you an example. This is a snapshot of omega bar over the entire domain. And the second row, I'm showing you basically the omega bar inside this box. This is T. This is the SGS transfer function from the filtered DNS data. So we can treat this as the truth. And we need that while it's mostly red, meaning that we have forward transfer. We have transfer from the resolved scale to the unresolved scale. Basically, we have diffusion. We see that there are also some regions that are blue. So these regions that are blue, this is basically backscattering, when you have transfer from the unresolved scale to the resolved scale. And we know that backscattering is important in many problems in engineering and also in weather climate modeling in the ocean circulation, for example. There's been a lot of work in trying to account for backscattering. Now, the diffusive models, they only account for diffusion. So as you see, like, for example, this is from a dynamic Smogorensky model, which is actually better than a Smogorensky model. It's a basically newer model. It's still, it's red everywhere. So it only accounts for forward transfer. It only accounts for diffusion, but it does not account for backscattering. So one of the interest in, at least in some disciplines, has been to use machine learning so that we can develop SGS models, data-driven SGS models, that not only may capture diffusion better, but also can capture backscattering. So to do this, the work that we have done, we used CNNs. This is a non-local data-driven SGS model. By non-local, I mean that we take the input is the result flow from the entire domain, and the output is the PyTerm from the entire domain, and we try to learn the relationship between them. I'm not going to go through the details of the CNN, but basically we use the DNS data to train this CNN that has 10 layers. Now, these are the results from an offline test or from an a priori test. Basically, when we did this test with this input and output, this is the first column shows the transfer from the truth for one snapshot. The second row shows the results from CNN. Now you see that the CNN is doing a great job, especially if we zoom in, we see all these little details of the PyTerm is reproduced by the CNN. The third column shows the results from an artificial neural network, not a convolutional method. This is a local model, which basically is from a paper that was published in JFM a couple of years ago. So basically, this is a local model. It takes a look at the SGS at a few adjacent breakpoints and learn the relationship. We see that this model also does a good job. And then again, this is the Smagorensky model, which does not capture backscattering. We can look at the average of the correlation coefficient between the PyTerms of the truth and what comes from these models. And we see that the ANN and the CNN have high correlation coefficients. So in the offline test, you can say this is a sort of an accurate model. Well, CNN is more accurate than the ANN, but they both seem to be pretty good. Now, we already heard from Stefan that online performance is not necessarily the same as the offline performance. And that's even observed in these very simple problems, single physics, very idealized model. And it's still, for example, in this paper, it was shown that if they couple this ANN with the coarse-grained solver, it's going to blow up. And many other people in the turbulence community have seen that for isotropic three-dimensional turbulence, again, very simple turbulence test cases, we had the same problem of offline results being good, online models blowing up. And so, for example, in this paper, what they did, they basically killed backscattering. So they did a post-processing, whatever PyTerm they predict, if it's positive, they keep it. If it's negative, they set it to 0. So they just make their model diffusive, and then it becomes stable. But of course, you lose all the advantages you gain from doing this non-parametric learning. So for our results, we also try to first, before moving to looking at the results in the online test, we did some tests when we changed the number of the training samples from 500 to 50,000. And we look at C, we'll see that even with 500 samples, C is like 0.78. Of course, it increases as we increase the number of samples. But then we look at what happens in the online test. And we'll see that when the number of training samples are small, we get instabilities, the type of instabilities that Stefan talked about. Maybe the whole simulation blows up, or you get very unphysical results. And especially in the case with 10,000 training samples, even though C is 0.9, we'll see that we have these instabilities. So we did another test, which is we calculate this correlation coefficient, but with the grid point separated based on whether there was diffusion at that grid point or backscatter. And one thing we observed was that diffusion is overall learned well, even with a small number of samples. It's really the backscattering that when you do not have a large number of samples, it's learned with a lower accuracy. So here the correlation coefficient is just 0.56 when you have 500 samples, but then it improves when you increase the number of samples and gets to 0.9 or here in 0.85, and this is the first time we see stability. So basically what these results tell us is that backscattering is harder to learn data-drivenly when the training set is small. But also, one thing we can speculate is that this disproportionately low accuracy for backscattering is the reason for instabilities, at least for this problem. But again, the point is, once we go to these large training sets, we have a stable online results without doing anything to the model. And then the model is also accurate. I'm not going to spend much time on the accuracy for like short-term forecasting. It's better than any of these other models. If you look at the relative RMSE of vorticity versus time. Also, if you look at the snapshots, the CNN captures a lot of the small details. We can look at the long-term statistics. If you look at the spectrum, again, we see that the CNN matches that of the truth pretty well. Perhaps the place to best see the advantage of CNN is looking at the PDF of vorticity. So on the x-axis, we have basically vorticity anomalies in terms of a standard deviation. And we'll see that the blue line, the CNN, matches the truth at the tails, while all these other models are too diffusive and they are within the sum. Now, so we have a stable, accurate online LES model, but then the next test is, can this generalize? And the answer is that it does not. If we increase the Reynolds number, the model does not work very accurately. So here is the result of just looking at the spectrum. So if we are doing the testing on the Reynolds number of 8,000 and the CNN is trained at 8,000, it works pretty well. But that CNN trained on 8,000 does not work that well if we go to the Reynolds number of 64,000, which is this red line. So to answer this, to solve this problem, we started looking at transfer learning. So the idea of transfer learning very quickly is that so far what we have done, we started with a neural network that was randomly initialized. We took n samples from a given data distribution from a given Reynolds number, and we did the training. Now, let's say we want to look at use this data-driven model for a flow that has 8 times higher Reynolds number. But let's say we don't have another 50,000 samples. But we can only take 500 samples, like 1% of that, and retrain that already trained neural network. We are not going to initialize things randomly. We are going to use the already initialized weights, and we might also only train some of the layers. We have already used the transfer learning in some of our earlier work. It's something very robust, works for RNNs, ANNs, anything else. Here we use it for CNNs, and what we did, we only retrained the last 2 layers. And once we do that, then the model generalizes as well. Again, we use some data from the new system, for example, at the Reynolds number of 64,000. Now we have this transfer learned CNN. That is, the baseline is that the base is that it was trained on the Reynolds number of 8,000, but then it works pretty well. That is this dashed red line here. We can even go to higher Reynolds numbers and even different resolutions just by adding an encoder-decoder architecture. I'm going through this pretty fast, but again, I'll be happy to answer questions, and we have the paper on archive. But we can go to even 16 times higher Reynolds number and still get the data-driven model to work well with only 1% of the amount of original training data. We also have done this with a one-dimensional Force-Berger's turbulence model that, again, with transfer learning, it generalizes. This problem is complicated because it has the shock waves, but again, with increasing the number of samples and doing data augmentation in this problem by taking the advantage of the periodicity in the domain, it became a stable. And these results are actually published in the Physics of Fluids a couple of weeks ago. So to summarize, the takeaway is that stability might require large training sets. And just by looking at the offline performance, even in these sample problems, we may not get a sense of how the online model would work. And the instability might be due to the inability to learning some aspects like backscattering. But then transfer learning can be something very helpful because we can have the large training set from a simple system that is just a base system, maybe simpler to simulate. We are currently pursuing a number of ideas in terms of how to reduce the number of training samples. Data augmentation is one idea. The other one is to include physics constraint in the neural network. And there have been a number of nice papers on this, for example, by Tom and Stefan and Mike and others. We also have a paper that was led by Kartik Kashinat about many different ideas of how to add physics into the neural networks, not just through the loss function, but also by, for example, changing a unit architecture to include some physics in it through a transformer that described in this paper. Maybe I have like 30 seconds. So I just want to mention that, as Stefan mentioned, online training might be a way to actually solve the problem of instability, increasing the accuracy and things like that. So this is something we have been thinking about. I'm going to stop here, and I'll be happy to answer any questions.